How to design self-reinforced nozzles? Welcome to our static equipment design channel. We provide professional training in static equipment design. Courses offered. Master, Pressure Vessel Design, as per ASME Section 8 Division 1. Master, Tall Cylindrical Tower, or Column Design. Master, Heat Exchanger Design, and TEMA Requirement. Master, PVElite Software. Master, Storage Tank Design, as per API 650. To learn more, register with Learn More link in the description, and apply coupon code MASTER15 to get amazing offer.
So there was one question in the group. So how to model this SRN nozzle in PVElite? I think I have also some relative.
Yeah, so we can just see that also right now because we are already talking about that. So let us model. We have already made a. I hope you guys can see my screen. Guys, screen is visible, right?
Yes, sir.
Yes. See now, you might have been using these 4 types normally. Okay, these 2 types are for set-on. This is also very rare. So mainly we'll be using set-in type of nozzle, 1 or 2. Now, if you go to this 5th one, this you see, if you just keep your cursor there, you'll see the type integrally reinforced type. Okay, and this is with lip. You can see the lip here. This is what I was trying to make. So
yes, sir.
This is a nozzle from forging with lip. The second type is it is integrally reinforced, but there is no lip. So finally welding will be groove weld. Okay, so you will not be able to do 100% radiography, but it is integrally reinforced. So these 2 are different. Okay, here you get 100% radiography. Your forging diameter is quite large in this. Okay, so the integrally reinforced with lip is even more costlier than your normal integral. Okay, it may be 1.5 2 times costlier because your whole dia becomes really large. Okay, so normally scenario for you will be to provide a self reinforced hub type nozzle. Okay, so if you select this is not lip type. So you see other things are completely same what we did for other nozzles. The only change here is you have to provide hub thickness, hub height, and then the bevel height. Okay, all this is hub thickness is what? You can just press F1 also and you will be able to see that. It has opened in the second window, so I'll just bring it back. So okay, I just pressed F1 and you can see all the definitions. Like sometimes you may struggle to see which thickness it's calling hub thickness. So this is your hub thickness, this is hub height, and this is the bevel height. So these are the 3 additional inputs which we need to provide. What is the thickness of the neck in this case, guys?
The same thickness that we have for the normal nozzles.
Yeah, so I'll just tell you because that also becomes really confusing. Then we forget this is not the nozzle neck thickness. What is your nozzle neck thickness in this case? This is your nozzle neck thickness. Okay, so whatever data you have provided for in this location, that is for nozzle neck. Is it making sense? Is it for nozzle neck? And here we are providing for hub. I hope I'm making it clear, guys.
Yes, sir.
Yeah. So now if I have to qualify this, let us first give that all. See, mostly if it is hub type, your nozzle neck will be in forging type. So you have to first of all select the material which is for forging. Okay, so you'll have to start from there. I'll just delete that sketch part. Yeah, So now if I have to, what will be my forging material, guys? If I have to make a nozzle from forging?
105, SA 105.
105?
Yes, sir.
For pipe also?
So yes, sir, pipe also.
See, 105 is used for standard
Ranges.
flanges or standard parts. Okay. If it is not standard, then which forging you will have to select? See, in that case also there can be two different kinds. See, if you have not gone to the material section, you just go through that again. See, one more thing I like to highlight at this point, that this course which you are referring, many of you might be thinking that if I go one time, that is good enough. Okay, that is good, but if you do it 2 times, 3 times, your takeaways will be more. Okay, so actually it is expected from you to, if you read it first time, you may be able to grasp 20, 30, 40%. If you go second time, your learnings will be more. It will be at 60% level. You have to at least revise once, at least 2 times you should go. That is the basic thing. Then you'll be able to catch up many things and you will remember it also for a longer time. So once I talk about forging, forging is also for 2 different types of application. One is the forging for normal temperature, and the second is forging when we require it to be qualified for low temperature. Okay. Now remember, this is forging, so thickness is very high. So impact testing becomes really important. Okay. So if you have to select a material which is good at lower temperature, then your forging selection will be different. If you have to select a forging for normal application, your material selection will be different. So can anyone
low temperature means when you go for SA 350 LF2, sir?
Yes, that is really correct, SRN. Good. So if we have to select a forging which is good for low temperature, we have to go for SA 350 LF2 forging.
Okay.
Yes. And for normal temperature or normal application, if low temperature is not a critical point, which forging we take?
Normal means SA 105. SA 105 also we can use.
105 we can use. So normally what we do, we take SA 105 standard part which is already available and then machine it. Okay, that is what generally fabricators do, because SA05 mainly you will not get forgings manufactured with that. All that is made for actually standards. If you just open that, I'll just open it for you. So that will make more sense because you always relate it with the code. Okay. So let us see what code is saying, whether by seeing the code, if we can make some differentiation between what we are saying. So if I go to SA 105, okay, what it is talks, where I went to find this SA 105?
Carbon steel.
Section 2A. Part 1, part 1.
ASME section 2, part A, and in
part
that, because of longer, too many specifications, that is divided into 2 parts. So we are in part 1 because 105 comes into from starting to 450. It's in part 1, and after that 450 is in part 2. So we are in section 2, part A. Okay, and first part of that. So when I go to specification, what it reads, specification for carbon steel forging for is it lighting some bulb to you?
So
This is for piping application, not for pressure vessel parts. Okay, that means, see, for standard flange you can consider as piping, but your nozzle or a girth flange which is coming in your vessel, that is not a piping, it is a pressure vessel. So this 105 is always made for piping application, not for pressure vessel. If I have to select a forging for pressure vessel, then which standard it will be?
The 266.
266.
SE
Right.
266 and
Correct,
266.
correct, correct. Very rightly said. So it is 266. Let us open that and see. So if you go to 266, you see same specification, means same description, only that here it is pressure vessel component.
Correct.
Okay. So if you have to make a forging for pipe, see, pipe means what we are talking about, it's nozzle of a pressure vessel. So actually it's a pressure vessel component. It's not a piping component. Okay. It is within the boundary of your section 8 division 1, which is applicable for pressure vessel. So if you are selecting a forging for that, you have to go for SA 266. Okay, fabricator, take 105, machine it to the required shape and use it. That becomes sometimes, cost effective. But if you have to qualify that job for use stamp, you will not be able to do that because that is not the right material. Making sense, guys?
For low temperature pressure vessel components forging, we use SA350.
350. If you go to 350, that also we can see 350 is also there. So if you see here, this is for carbon as well as low alloy. Okay, requiring notch toughness testing. Now this is again, you can see here for piping components. Okay, but still for pressure vessel also we use the same material. Might have been.
So what about SC765?
765 I've rarely used, but we can see that what it is written. I have not used 765, but see, there can be lots of different material used in different industry. The material itself is a science, you can go deeper and deeper, still lots of things to learn. So if 765, if you see here, specification for carbon steel and low alloy steel pressure vessel component forging with mandatory toughness requirement. So if the toughness requirement is mandatory for a pressure vessel component forging, we should go for 765. Okay, who told about 765?
No, sir. I have seen that 765 is, it's been using with the low temperature vessels.
Correct. It is true. That is made for low temperature pressure vessels and pressure vessel component forging. So just if you have any doubt, just go to that specification, and if you read that, it will give you lots of information. Just the description, we have not seen in the detail, but just if you go to description itself, it is making many points clear. Okay, guys. So now in our case, we just started with the first point. So you see here, every point, it looks simple question. So sometimes when you ask a question in WhatsApp, it really makes for me a little difficult to answer that from where I start. Okay, because always I have a habit of explaining things from basic. So see, anytime if you feel your question is not answered to your satisfaction in the WhatsApp group, keep that question for later, where we can discuss it in the live class. Okay, so the query you have maybe for others also the same query may be there. Okay, so we have selected that forging material. Now if it is forging, you don't have to go with schedule. Okay, we can just go with the actual dimensions, and like if it is 6 inch, let's go with 6 inch based on ID or OD, anything you can go, and whatever actual thickness you are selecting, that you can give. Okay, so 20 is failing, 25. We'll have to give others also, then only we can see whether it is failing or not. Let us provide all the inputs and then see. Okay, radial nozzle projections, everything is okay. Now hub thickness, what should be my hub thickness? Now I hope you know what it is, what hub thickness is. You're talking about this thickness. Okay. So what value I should take, guys?
So any random value more than our nozzle thickness.
Yeah. So let us take 40. Now you see, now if I try to reduce this, because see, before providing that hub thickness, if I'm increasing this, there is no point, because finally hub thickness was smaller, right? So it was failing here. So you could see that failure, but it is not that this is the thickness which is required. Okay. Now if I reduce it to 12, see 12 is also getting qualified. If I make it 10, 10 is also getting qualified. So if I keep this as 10, I'll keep this as 20. 20 is not getting qualified. So I'll just take it 25. Let us make hub height also. Hub height, what I should keep?
Sir, hub height shall be more than the reinforcement limit.
It will depend upon what reinforcement you require. Okay, so you can see here what is failing is the reinforcement. Making sense what I'm trying to say? Finally, your hub height will decide how much reinforcement you are giving, because your reinforcement is inbuilt in that. Right? This is providing you the reinforcement. Are you guys getting it?
We have the vertical reinforcement limit.
Yes.
So we shall give the hub height more than that, so we can get that one.
Yeah, up to that we can keep. Other than that, you can, like, your limit for reinforcement can be at this point. Okay. After that, even if you provide after that, it is of no use. So why unnecessary waste the material? After that, you can provide your bevel, bevel you can start, and then your neck thickness will start. Okay. So I'll come back. Then let us clear this. Okay. So 100 mm bevel height, you can see in ASME there is a particular angle mentioned for this bevel height. Okay, if you see that UW, you will get that value. So, and if it, even if you use this obtain ASME bevel angle, you can just click on this. It will automatically change this dimension. So if you want to round it off, you can do 90 and 10. So it will be very close to what angle which is given. Then the rest of things are okay. You can just put okay. Now this is your nozzle with self-reinforced. Okay, guys. Is it clear? Now, if I just change it to...
So how I give the 90 mm height basis of that?
There's no basis. See, if you just see that what is the upper limit, based on that, you can reduce. Now, let us come back to that and just what 20 mm I had given and that 90 mm. And this was 10, right? So 20 or 30 it was. See, because if I last time 20 we had given, yeah, 20, 90, it's passing now. So now you can just keep on. See, you can see here what is the area you're getting and what is the area required. So 851 is required and your area is 1199. So if you keep on decreasing, okay, your area like 80, let's say 50. Okay, still we are, I think, beyond, because the thickness, normally the thickness is very small, right? 12 mm. So what is the limit for vertical normal direction nozzle reinforcement?
2.5 of thickness.
2.5 times thickness. So if we do 2.5 times thickness, so 24 and 6, 30.
25.
So if I take 30, then now you see still 119. Now if you reduce from here, then your area average will keep on reducing.
Yes, sir.
So like that you have to give. So 20.
So for optimum design, we shall take is more than the 25, but up to the 25.
Yes, more than 25. See, because not only your, see, finally, if you're providing reinforcement, you see this also length becomes critical. So your finally neck thickness has to have a proper projection. So your neck thickness, you have to increase so that not thickness, but length of that neck. So that finally your projection is exactly where you want.
Okay.
So, and if you're providing hub, we generally keep it almost half of that. Okay, we don't give it like such a small hub. See, because finally what is happening, you are getting a forging. Okay, that this is also really let us discuss that also. You might be thinking that why to provide extra, but that is otherwise. If I have a nozzle like this, let me just this is my nozzle. What finally we wanted is that this forging we want. Okay, this is the final shape you want, and for this shape you will not get this shape, right? You have to order a forging of what I have made.
Okay.
Making sense, guys?
Okay.
This is the hashed portion you want. Okay, and you have ordered a forging with this shape. So finally you have to machine it to this shape, isn't it?
Okay.
So if you have to machine and remove, so why not to utilize the maximum thing, right? So and your machining activities also, it will benefit you to give higher thickness here. Okay, it is little otherwise. Normally to provide higher thickness, we have to spend money to provide higher thickness. It is costly, but in this case, it is costlier to remove material because that much machining hours will be added. Making sense, guys? That is the reason you always see that self-reinforced nozzles, you will see the proportion of hub is quite large.
Yes, sir. Okay.
Okay, got it. So you don't have to bring it down till here. You can just, because anyway you have to meet that projection of that nozzle. Because if you don't meet that, your boltings and all will become really challenging. So we keep that, instead of making all the nozzle neck and machine to that nozzle neck thickness, we provide that hub. Okay, I hope it is making sense now. Okay, so now if I hope this type of configuration is clear. If I just change it to the other one with the lip type. Okay, now you see here only that hub thickness and how wide it is, what is important. So what is my hub thickness in this case? Which is my hub thickness first of all? So you can again press F1 in PVElite and see what is your, again same opening, same diagram is opening. So now let us see some different configuration they have mentioned. See, for that ASME angle, they have provided some, the 30 degree for division 1. That is the limitation for your this angle. Okay, cannot be more than that. That is all based on your 1:3 taper. Finally, if you see 130 degree means it will come to that value. Okay, so now if I have to provide a hub thickness, so hub thickness is your this thickness. So in this case, what will be my hub thickness? Till here, this point. Okay, if I draw it for that case, we already have this. So yeah, just draw it. So if I have provided a hub like this, my hub thickness is this point. Okay, so If I'm taking that hub thickness like that, let us take is 30. Hub height, at least 25, 30, same philosophy. Okay. Now if it again 30 and this is not meeting, no, it's meeting actually. See, sometimes the PVElite takes some times to recalculate. So you have to just wait and press tabs so that it will adopt to the values which you have provided. Okay. So now you see that average what you have provided is much more than what is required. So it is okay. Okay. Now if you can just plot it also and see how it is coming, that we'll have to change that. Fillet will not be applicable for this case. Okay. So you can see here that limit is also indicated. See here. And you also have to remember that it is not 12 actually over there. Required thickness is even lesser than this. Okay, so your vertical normal applicable reinforcement limit is even lesser than 25. So now if you see this, okay, nozzle to shell groove weld will not be there. You can select the different configuration as per ASME also. Based on UW, you have lots of figures, right? So that option is also available for nozzle designation. You can select. Okay, so is it clear how we do it for different self-reinforced type of nozzles? When to select lip and when to go for normal?
Sir,
yeah, go ahead.
Here is the in the lip type nozzle hub thickness is up to the weld from
up to this point, yes. Not up to the weld, but where that your taper is starting.
Okay.
Okay, so this, like if you have provided a nozzle, it is like this. It may be even some straight portion, and then your hub, the taper is starting. So in that case, this. Okay, if you don't have any straight portion starting from here, then again this point.
Sometimes we have the multiple tapers, like 2 slopes.
Yeah. So 2 slopes, then you have to consider the first one. Okay.
First one. Okay.
Like sometimes it may be even like this. Okay. So this will be your applicable hub diameter. So it is from where the taper is starting. Okay.
Sir, if we are taking from the first part, then actually we are not having the reinforcement available up to above that point.
No, not available above that point means?
Like if our vertical reinforcement limit is above the tapered line, the blue line. So like this, yes.
Yeah. Then
so we are not having reinforcement in between the proper complete reinforcement.
Why? See, whatever area is there below this line, all will be considered for your reinforcement. It is not like this is the point where the reinforcement is limited. It will be calculated up to this point, whatever reinforcement you have provided. All will be counted.
Okay.
Even it is going beyond, like if you're not given any, see, it does not matter what words we are giving, that does not matter. Finally, basic is whatever area is coming below this line, it will be considered as reinforcement. How you provide the shape, what is hub, what is taper, it is not dependent upon that. That is the words which we have given. But the basic is that reinforcement area, whatever was required. Apart from that, whatever you have given, whether it is by means of weld, whether by means of additional thickness, everything will be part of reinforcement. Okay. Great.
So in that case, we need to perform the WRC or not required?
WRC for which, like for this nozzle you are saying?
Yeah, yes, sir. for SRN 14, sir.
You can perform WRC. There is no challenge in that. Finally, it is cylinder to cylinder junction, right?
Okay.
So WRC is not a problem.
Sir, it is must.
Not must. WRC already depend upon whether loading is there or not. Whenever external loading is there, then you have to perform WRC. It is not dependent upon the type of nozzle.
Okay.
Making sense, Saran?
Sir, actually, code is not given the rules for the WRC. It is our call to perform that.
Yes. And definitely, see, WRC means whenever there is external loading, then only WRC comes into the picture, right? Otherwise, see, code is simply saying whatever loading is coming, you have to take care. Code is very clear in that. Okay. Code simply says that you have to find your own standards and methods with which you can satisfy your authorized inspector. Okay, so the statement is very simple, but it is trickier, unless you select a method which is very widely used, it will be difficult to satisfy that AI, right? Because AI has been doing this checking of this calculation. So whatever he might have seen, he will prefer to that method. So if he has seen WRC calculation for external load, he will like to see that. If you have done by some other method, he will ask lots of questions. Why he did, why that, So it will be difficult. You have to argue and then you have to convince him. You have to show each and every step. Okay. And if you have done based on what he has already seen, he'll just, okay, you have done WRC. Okay, it is okay. So he'll be happy with that. He will not go into that detail. Making sense?
Okay.
Yeah. Any other question, guys? I hope you guys are able to understand what we are talking about.
One question I had, sir.
Yes.
Earlier we just talking about that self-reinforced nozzle. There is a in a, I think client spec, there is a one point they are specify that hub thickness ratio, hub thickness to the cell thickness ratio, something we have to maintain, like 3 times or 5 times.
See, always client may give some additional specification based on their, good engineering practice. So if specification is telling you something like that to, you have to follow that. But there is, if you ask that question, why that is coming?
Yes, why that?
That is really difficult to answer because that is based on good engineering practice. So it may be because WRC, it may help. I don't know. It's really difficult to answer why they have strict to that statement that it has to be 3 times or 4 times.
Okay.
So
it is related to the stress concentration or something.
So good engineering practices are really difficult to even justify and challenge that, because anytime you can ask why 3 times, why not 4? Okay, so if you just ask to the client also, they will struggle to give you that answer, that why, because they might have been following for a very long time. They might have used that configuration in their normal plant and they want to follow that. Okay. So many of it might be based on what they have already seen and it is working. That becomes a good engineering practice. Unless it is for some reason it fails, then they will ask question, oh, we followed some good engineering practice, but it's not correct. We have to build some additional factor. So like that also many things are there.
Okay.
It might be due to stress concentration, what you asking. So unless we have, a contour which is very uniform, transition of 2 different thicknesses, if it is not uniform, there will be stress concentration built up in that area. So if you're talking about sectional division, we never bother about stress concentration or peak stresses. So that anyway does not come into the picture, right?
Yes.
Only we do FEA, that time you'll be able to see what is the stress concentration, what are the stress razors which are there in your shape.
Okay.
Any other question, guys? Adnan, you're back.
Yes, Mr. Abhishek. Yes.
Yeah, they're right. You understood. We discussed a lot about this SRN and the lip type.
Yeah, I understood. Thank you. I actually in the work, so I cannot talk, but I understand. Thank you.
Okay, great. I hope you understood that. So in which criteria? So the only point is that whenever client is asking, that time you will go for lip type because those are really costlier. Okay. Okay, guys. Any other question?
Hello, Abhishek. Is my voice audible? Hello.
Yeah, Jairam. I can hear you.
Yes, I had a small query. Initially, we discussed for 2-inch and lesser nozzle. I think for small bore connections, we provide stiffeners, right?
Yes, correct.
And higher, we do the stress analysis and try to qualify the nozzles for that. But for these lower nozzles, in case if any instruments or any other analyzers are connected to this nozzle, generally, I haven't seen any specific calculations or qualifications for this. So how is there any calculation for how the stiffness need to be? I think you said there will be 2 stiffeners or at 90 degrees. I think 120 degree 3 stiffeners are also being used.
That also mostly 90 degree apart is mainly used, but definitely it can be 3 also. That all.
But is there any calculation to qualify this? Because my only concern is I haven't seen any calculation. My specific concern is for bigger analyzers or something for stack, which need to be placed. And do we need a separate supporting for this analyzer load, or can the nozzle take this? How do we ensure that?
Correct. Okay, I'll answer that. See, first of all, whenever we are doing nozzle calculation, okay, as per code, you have to calculate for whatever pressure, the thickness you have to evaluate based on UZ 45. Okay. Apart from that, see, that is about pressure as a loading. So if you consider pressure as a loading, it does not matter whether it is attached to analyzer, it is a process nozzle, or it is instrumentation nozzle. The methodology is same for all. Okay. But now code also talks about that if you feel that there are some additional loads coming due to some reason, maybe the analyzer which is very heavy and it is attached, and you feel that that load of that analyzer or agitator, my nozzle will be able to take. Okay, so for that you have to perform finite element analysis. By doing design by rule, it's really difficult, okay, to find a formula which will suit to that application. So when I talking about stiffeners, which we provide two numbers at 90 degree apart, it is all based on good engineering practice. There is no calculation which we do to support that in division 1. Okay. Am I making sense, Jairam?
Yes, but this is what I have also observed. But this is a good engineering practice we follow. As such, there is no calculation. That is
no calculation. So if you feel that there is something which very heavy, and you feel that it may be a problematic, okay. So first of all, you can convert that into external load and check with WRC. Okay, that is the one thing which you can do. Okay, and strengthen that nozzle based on that. At least something similar. You will be able to justify that I have converted that, because definitely that question may be asked by AI. That this is a quite big load. How you have taken care of this load? So now, if you have converted it into a nozzle load and applied that load to the nozzle, qualified with WRC, that becomes a standard procedure. Okay, you can do the calculation now. So that is somewhere at least you can say that, okay, I have considered this. So your AI may be convinced with that. And if the AI is saying, no, this loading is not only vertical, it can be this direction also, and that configuration cannot represent, then you will have to perform finite element analysis. If it is complicated, like agitators, some dynamic load is coming, okay. So in that case, it may be difficult to justify with WRC. Making sense? So if you are providing stiffeners, that calculation you cannot justify with WRC. You may increase the thickness, provide additional pad, OD you can increase of that nozzle. That configuration, if you are just changing, you can justify that with WRC by providing additional load to that nozzle. Making sense?
Yes, Abhishek. And initially for the agitator you mentioned, for the stiffness, some calculations were there for the dynamic loading.
Yes.
What was the reference to?
See, difference was that, like, if I have a vessel which is loading some agitator, agitator is loaded on that. What example we took was, it's a vertical vessel. I'll just draw it for you. Let us make.
No, my question was if there is any standard or any code for that calculation or equations to be used.
The equation you have to use is Rourke formula. Have you heard of that book?
No, sorry.
Okay. So that book I'll just share with you or in the group itself. Okay. So that you guys, Rourke is a very important book and you will find lots of different types of formulas in that Rourke, and you can just convert your problem matching with that. See, definitely you may not be able to get the exact thing, but at least if you are able to simulate and conservatively, you can find some formula which may be conservative for your case. Definitely with that you can justify to your AI or your client. So that is a very good book. So just go through that and let us see if you are able to understand. Okay. Once you see, in the first time when you see, it will be difficult for you to use that, because there will be lots of formulas and you will stuck that from where it is taken. So I'm just finding that book and I'll share it so that I don't forget.
Sure, Abhishek. Thank you. I'll go through that.
I have just found it and shared in the static community group. Okay. So just go through that, and for that, like if it is a flat plate or circular plate, you will find the loading for each type. Like if pointed load at the center, uniformly distributed load on the plate. Okay. Or even in varying with some equation, all the different configuration you can find in there. Okay. That is a very good book to follow.
Okay, Abhishek. Thank you.
Great. Thank you. Any other question, guys? Anything which is bothering you? And you
Sir,
want
one thing I have to ask. In flange design, for appendix 2, we are designing with respect to the operating basis and
hydro test.
Yes, hydro test basis. So in our standard flange, what was the basis for that flanges? Because if we are going to design that same flanges, so
it does not qualify. Yeah, I'll tell you the history of that. See, the standard flange were made when we didn't have that formula for calculating the thicknesses of the flange. Okay, you got that? When we made that standard flange, that time we could not validate that with the available tools of mathematics. No FEA, even design by rule, was also not developed at that extent. So what was done, that they took some conservative approach. They made some flanges, used that, okay, for different pressures. It was, the practicals were done, made that flange, keep on increasing that pressure and see at which level it is able to take that load. But all pressure temperature rating which you see with it is all developed based on actual experiments. Okay, so it's all practical driven dimensions, not method calculated theoretically. Okay, so standard flange, you should never qualify with. If you see the code also, it says that you don't have to qualify the standard flanges. Okay, you don't have to design that again by mandatory appendix 2. Mandatory appendix 2 is only for non-standard flanges. Okay, so standard flanges may fail in even bolt spacing or thickness, hub thickness. So, but standard flange is to be selected based on pressure and temperature rating. And if you are selected based on that, it is good enough. You don't have to design that. Have I answered, Rohit, to your question?
Yes, sir.
So the standard flanges are not designed. See, that is how that 16.47 series B came into the picture. When we had the tools to do FEA and the normal design calculation, then for larger forgings, for above 24-inch, it makes really a huge difference, right? 24 inch size is very big, right? So if we have already the methodology now, why not to reduce that thickness? Okay, so that exercise was done and series B was developed, which is much thinner than your standard flange. So you see now for B 16.47, we always go with series B because that will give you very, thinner flanges.
Yes.
Okay. So that is now like standard plus design methodology added and verified. So now, about smaller flanges, it does not make any difference because everybody, if you are changing any standards, so based on these standard, lots of company has made some dies, everything is now stabilized. If you change that, it will be very huge change for the industry. So they will not like to change that. And all these standards are already driven by manufacturing. It is made for the manufacturing people. So unless it is convenient for them, it is not going to change that. So definitely for smaller sizes, it does not make any difference if little bit higher or lower. So we are keep on following for smaller dimensions, same thing which we did 100 years back.
Okay. Good.
Great. Okay, guys, lovely discussing with you. So shall we close it here now?
Yes, sir.
Hope you liked the content. Subscribe the channel to get access to lots of such content. If you want to purchase the full course, go to the link in the description and register.